All right, I'm going to go ahead and go through and finish up these problems from chapter 13. It was getting to be a little too long and too many interruptions and how long my videos were getting and stuff is getting messy. So I'm going to do these now where I worked them out ahead of time, and I'm just going to talk through them so hopefully it goes faster. Pause it, rewind it, do what you need to do to hear what I say again and go through it. But I'm basically going to go do it. So I drew a picture here. We've got the bullet right here. Maybe I'll use this. We've got the bullet right here, headed towards the mass hooked on a spring on a frictionless plane. Now, the first collision that occurs is what is called an inelastic collision because the bullet is going to stick into the mass. In inelastic collisions, energy is not conserved. So we cannot just do this straight out of the gate with conservation of energy. We need to actually figure out what happens through the collision through conservation of momentum. So that's what I do here. Initial momentum equals final momentum. The bullet has an initial momentum. The block and mass does not. It's sitting there at a velocity of 0, so it cancels out. And then afterwards, they move as one, so they act like one mass, which is just their two masses added together and their final velocity. If you rearrange this, do some algebra and solve it, you get that the final velocity after the collision, just immediately after the collision, is that right there, mv naught over their total mass, little m plus big M. Now we're going to go over and do conservation of energy. We're going to take the kinetic energy that we got after the collision, after we lost some energy due to heat in this inelastic collision, and we're going to do conservation of energy for how much will the spring compress. So we know that mechanical energy initial has to equal mechanical energy final. And so our kinetic energy initial plus our potential energy initial equals our kinetic energy final plus our potential energy final. Now, initially, it's all moving and the spring is not compressed. So initially being right after the collision, we only have kinetic energy and we have no potential energy right there. And so that crosses out. And then after it fully compresses, all this kinetic energy is gone and we have nothing but potential energy left. So that means we get 1/2 mass total, their total mass, times that initial velocity right after the collision squared equals 1/2 kx squared, which is k being the spring constant. Now, I can go ahead and solve that for x, so that's how much it will compress, and that equals the square root of the total mass divided by the spring constant times that initial velocity. So just do a little algebra to solve there for that. The total mass here in that equation is the sum of their two masses. The initial velocity in this equation is actually this final velocity from over here. And so I'm going to take that, and I'm going to plug it in right over there, okay? And that's mv naught over their total mass, little m plus big M. So I plug those back into this up here, and it gives me this. And then I just do a little rearranging, and I do a little canceling out and stuff, and combining of those two fractions, and I get that as my answer right there. mv naught over the square root of k times the sum of their masses. All right? And there's no numbers to plug in on this one, so that's it. So that's 13.3, or 13-13. And now we have 13-14. Here it says a pendulum and a grandfather clock is designed to take 1 second to swing in each direction. So that is 2 seconds for a complete period. That's immediately they tell us the period is 2 seconds. Find the length of the pendulum that has a period of 2 seconds. So we're looking for L. So we know that T equals 2 pi square root of L over G. We're assuming we're here on Earth with this one. And so you go ahead and solve that for L, square both sides, divide by the 4 pi squared, multiply both sides by G, oops. And you get L equals T squared times G over 4 pi squared. Plug in your numbers right here, right? You end up with like 4, you have 2 seconds squared over 4, so those just cancel. And so, you know, these two will just cancel because it's 4 over 4. And so you end up with 9.8 over pi squared. Pi squared is around 9 point something, so you should have 1 point something or something near 1 as your answer here. But I'll leave it for you to go ahead and plug in. And when you do that, you should get your answer right there. And that's it. That's the final answer there, but you can plug that into a calculator. All right. Next one, 13-16, this is drop time. So this one is under the assumption that we are not actually maybe on Earth, but we're in a different location. And we're given a length of a pendulum, we're given its mass, and we're giving its period. Now, using that information, we can come down here and solve for what the acceleration due to gravity is. So I come down here and I use the t equals 2 pi square root of L over G. I solve it for G by squaring both sides and then isolating G. So G equals 4 pi squared L over the period squared. And then I just plug in those numbers. I plug in 0.627 for L. I plug in 1.59 seconds for period and square it and put that in. And I get about 3.1166 meters per second squared. After that, I bring it over here and just do the regular old free fall, but using 3.1166 as my acceleration. So delta y from your kinematics for free fall, delta y equals 1/2 gt squared plus the initial velocity times time. Here, the initial velocity is going to be 0. The height is, or the delta y is going to be 1 meter. And then technically it's -1 meter. And then G is really -3.1. So I probably should have put those in there. It's falling down. So there's my negative in there. It's falling down 1 meter and a -3.1. And so that when we plug that in, there's a negative there, and it cancels out. So anyway, you plug that in, you take this equation right up here, that one, you isolate it for t after canceling out VI because it was 0. And you come down here, you solve it for t, and then plug in 2 times delta y, which is the -1, over the acceleration we found right there, and then take the square root of it, and you should get your answer. So about square root of about 2/3, whatever that turns out to be. Okay, and then that'll give you your time. And you can look at your units there. The meters are canceled with the meters, and then you have 1 over second squared, which is just second squared. Square rooted is just seconds. So you'll end up with just a seconds there when you do that. All right, and that's 13-16. Now 13-17, which I think, yep, is the last one. So here we have a hula hoop that has a mass of 0.68 kilograms and a radius of 0.51 meters. Somebody accidentally bumps it and it starts oscillating back and forth. Now we know that from class that the period of a non-just pendulum bomb, but of an actual rigid body is 2 pi times the square root of the length of the rotation point from the center of mass times the square root of the moment of inertia over mass times the distance to its center of mass squared from its rotation point. So here in this case, the mass is 0.68 kilograms. That's given to us. The length to the center of mass is at the center of the hula hoop. So when you have the hula hoop here, right, it's rotating about here where it's hanging, and so the center of mass is there. So this is L right there, which is half, which I just realized I shouldn't have done as half the radius, huh? I should have just done that as R. What was I thinking? So let's make that correction in there. I was thinking diameter and I shouldn't have done that. And then I equals 2mr squared, because they give that to us right up here, right there. That's what I is. And then the radius is 0.51 meters. So now coming up here, I put R over 2, and that should have just been R. So this is R over G. And then over here, I put R over 2 again, and that should have just been R squared, which means this should have just been R over G. This should have just been R squared over that. And so what did I do here? I should have 2 up there, not a 4, right? So this should be 2R over G, which means this is 2 pi, 2R over G again still. And so then now I just need to plug into that. So this is 2 pi, and then, sorry about that, this should be 2 times that. If you ever see me make a little mistake like that in any of these, please point it out to me. But anyway, it'd be 2 times that. Plug that into your calculator and that should be right. I think I made that correction right. Double check my algebra on it, make sure I didn't mess that up by going through and changing all those R over 2s to just R's. I think I got it, but double check. Okay. And so that's it for that one. Plug that into a calculator and you should be done. Okay, so you have about 1/10 the square root of 1/10, so, and then times 2 pi. So whatever that turns out to be. Plug it in a calculator and get it done. All right, that's it for this one. So I'll get started on the next one.